Welcome to This Explainer. Today, we're diving into something that literally sounds like a sci-fi movie. We're going to explore how astronomers have pulled off this seemingly impossible. They've turned our entire Milky Way galaxy into a colossal scientific instrument. We're talking about pulsar timing arrays. It's this revolutionary method that lets us detect the most massive, invisible phenomena in the universe. And get this, we aren't doing it by looking. We're doing it by listening to the very fabric of space itself. So you're probably wondering, how on Earth do you build a gravitational wave detector the size of a galaxy? Well, actually, scratch that, it's not on Earth at all. By observing these incredibly stable, dead stars scattered across the cosmos, scientists are currently detecting literal ripples in the fabric of spacetime. And these aren't your quick everyday ripples. These waves are so vast, they take years, sometimes decades, just to complete a single oscillation. To wrap our heads around this massive concept, our explainer today is going to build from the microscale of a single rotating star all the way up to a stochastic background hum created by supermassive black holes. We'll be looking at nature's ultimate cosmic clocks, spacetime ripples, and nanohertz waves, the galactic gravitational wave detector, separating signal from cosmic noise, supermassive black holes, and beyond, and finally, the future of pulsar timing.
Part 1. Nature's ultimate cosmic clocks.
Okay. Before we can even begin to understand this giant galactic array, we have to start with its basic building block, the millisecond pulsar, or MSP for short. Basically, an MSP is the remnant core of a dead star. They're these incredibly magnetized, super old neutron stars that have been spun up to just wild speeds by sucking in mass from a neighboring companion star. They complete a full rotation in less than 30 milliseconds. And because they are ridiculously dense, we're talking packing more mass than our entire sun into a sphere just 20 kilometers across, these cosmic flywheels have a rotational stability that rivals the absolute best atomic clocks we have on Earth. As they spin, they shoot out radio beams from their magnetic poles. Every time that beam sweeps across Earth, we get a little pulse. It's exactly like a giant cosmic lighthouse. To put this insane precision into perspective, let's look at the number 0.340 microseconds. Over years and years of constant observation, the average error in predicting a specific benchmark pulsar's beat is just 0.340 microseconds. That is literally like predicting the arrival of a speeding train from thousands of miles away and getting the arrival time right down to a fraction of a single microsecond. It is just mind-blowing. Part 2. Space-time ripples and nanohertz waves. So why does this extreme, mind-boggling precision actually matter to astronomers hunting for gravitational waves? Well, gravitational waves are literal ripples in the fabric of space-time itself, caused by the acceleration of incredibly massive objects. When one of these waves rolls through our cosmic neighborhood, it physically stretches and squeezes the space-time between Earth and our pulsar. So if the space between us and the pulsar gets stretched out by the wave, that radio pulse has to travel a slightly longer distance, meaning it takes just a tiny bit longer to arrive. Conversely, if space gets squeezed, the pulse shows up a fraction of a nanosecond early. By tracking these super tiny advances and delays over years, we can literally measure a gravitational wave passing by.
Now, the really tricky part is figuring out how to isolate that signal. The delay we see in a pulse's arrival time is actually made of two distinct parts, the Earth term and the pulsar term. The pulsar term is the effect the gravitational wave had on the pulsar itself back when the pulse was emitted. That could have been thousands of years ago. It's totally localized and unique to that one specific star. But the Earth term, that's the physical distortion of space-time happening right here, right now, as the wave washes over our planet. And here's the absolute game changer. Because a wave passing over Earth shifts the timing of all incoming pulses at the exact same time, scientists can search for a coordinated, correlated signal across the entire sky.
Part 3. The Galactic Gravitational Wave Detector. This brings us to the totally ingenious solution of stringing all these independent stars together. Think of it like this. If one pulsar is a single metronome, a pulsar timing array, or PTA, is the entire symphony orchestra. Step 1 is to monitor a wide network of these pulsars, usually about 20 to 100 of the most stable ones we can find scattered across the celestial sphere. Step 2, astronomers track their times of arrival over incredibly long baselines, multi-year or even multi-decade. You need that much time because nanohertz gravitational waves take years just to complete a single oscillation. You literally have to wait years to see the wave rise and fall. Then, step 3.
They cross-correlate the timing deviations between all these pulsars. This isolates the shared gravitational wave signal from the random, independent noise of each individual star.
So how do they actually know for sure they've caught a gravitational wave? They look for a very specific mathematical signature called the Helling-Downs curve, first figured out back in 1983. This curve describes a predictable quadrupolar spatial correlation. In plain English, it predicts exactly how the timing deviations of two pulsars should relate to each other, based purely on how far apart those two pulsars appear in the sky. Spotting the specific Helling-Downs correlation across the whole array is the ultimate smoking gun. It is absolute proof that the timing shifts are caused by a stochastic gravitational wave background stretching and squeezing Earth, and not just some random cosmic static.
Part 4. Separating signal from cosmic noise.
But as you can imagine, space is incredibly messy. Finding a signal that's only a few nanoseconds long requires an epic cosmic detective story to filter out an entire galaxy's worth of interference. We essentially have to model and remove a chaotic mess of noise, which is broadly split into white noise and red noise. White noise is the short-term independent stuff. Think instrumental thermal errors at the telescope, pulse jitter, or random radio frequency interference. Red noise is the long-term low-frequency headache. This is stuff like the pulsar's own internal starquakes, literally sudden glitches in the star's spin, or delays caused by shifting clouds of bubbling interstellar plasma drifting between us and the pulsar. As you might guess, separating all this noise is computationally massive. You need serious horsepower. Traditional Bayesian software models are highly accurate but incredibly resource-intensive. But lately, novel frequentist frameworks like the Pint software package are proving to be massive game-changers. Pint can characterize the noise in a fraction of the time, using way less CPU power, which is absolutely crucial as our datasets keep growing larger and more complex. So astronomers essentially have to build an absolutely airtight mathematical model for every single pulsar in the array. They have to perfectly account for its exact motion through space, its binary orbit if it's dancing with a companion star, the dispersion of its radio waves, and get this, even the exact orbital movements of the Earth and planets in our own solar system. Only once the data is completely scrubbed of all this deterministic movement, along with all that red and white noise we just talked about, only then does the pristine, underlying nanohertz gravitational signal finally emerge from the dark. Part 5. Supermassive black holes and beyond. Now, you might be wondering, what exactly is out there producing these colossal nanohertz frequency ripples that take years to complete just one wave? Well, the answer is pretty breathtaking. Recent 15-year dataset releases have revealed 2 to 4 sigma evidence of a stochastic gravitational wave background. Think of this as a continuous cosmic hum. This background hum isn't coming from one single event. We're actually hearing the combined overlapping echoes of millions of pairs of supermassive black hole binaries. We're talking about absolute monsters, billions of times more massive than our own sun, slowly spiraling toward each other in the hearts of distant colliding galaxies all across the universe. There is this fantastic quote from Dr. Scott Ransom at the National Radio Astronomy Observatory that just perfectly hits the nail on the head regarding the sheer scale of what we're doing here. He says, "We are utilizing a gravitational wave detector spanning the entire galaxy, crafted from exotic stars, and it simply astounds me. Now we comprehend that it is the symphony of the gravitational universe." I mean, wow. That beautifully captures it, doesn't it? We aren't just looking at the universe anymore. We are finally listening to its grandest melodies. Part 6. The future of pulsar timing. The detection of this cosmic hum is really just the opening note of a much larger scientific revolution. To truly resolve the individual black hole pairs creating this hum, we need a lot more pulsars and much longer observation times. And the only way to achieve that is through an unprecedented level of global scientific collaboration. Enter the International Pulsar Timing Array, or the IPTA. This is a massive team-up, combining data from Nanograv in North America, the EPTA in Europe, the Parkes Array in Australia, plus arrays in India, China, and South Africa. By pooling their datasets, they drastically increase the number of pulsars we monitor, which sharpens our view of the gravitational wave sky. And the hardware itself is taking a massive leap forward, too. Next-generation mega-telescopes like the upcoming Square Kilometer Array Observatory, or SKO, are going to be absolute game-changers. The SKO will deliver 3 to 4 times the sensitivity of current Southern Hemisphere facilities. Instruments like this and the DSA 2000 will drastically increase the number of faint pulsars we can discover and track. We're essentially thickening the web of our galactic detector, allowing us to eventually pinpoint the exact detailed structure and origin of this cosmic background. Looking even further down the road, there are some pretty wild future concepts on the table, like artificial pulsar timing arrays. The idea here is to utilize a constellation of satellites carrying ultra-stable atomic clocks in orbit around Earth or out in the solar system. By doing this, we could bypass the messy interstellar medium entirely. We could create these pristine, noise-free networks capable of detecting intermediate mass black holes in the decihertz band. It would perfectly bridge the frequency gap between our ground-based detectors and current pulsar arrays. And the coolest part? It's not just black holes we're looking for. By continually refining our timing models and pushing our sensitivity deeper into the microhertz and nanohertz bands, we are throwing open a window to bizarre theoretical physics left over from the dawn of time itself. We might soon detect the oscillations of cosmic strings or boson cloud instabilities around rotating black holes. We could find gravitational wave memory bursts or even primordial spacetime fluctuations generated mere moments after the Big Bang. We have literally just gained an entirely new sense to perceive the cosmos. By timing the flashes of dead stars, we've turned our Milky Way into a giant resonant chamber for the universe's most massive events. So, as we continue to tune our galactic radio dial to hear the cosmic hum of supermassive black holes, it leaves us with one massive question. What entirely new, unseen phenomena are waiting to be discovered in the gravitational universe now that we can finally listen?